Hello and a warm welcome to this micro lecture on freezing. First, I would like to briefly go through the essential subject matter knowledge. A matter can exist in three different states, namely a solid state, a liquid state, or a gaseous state. For example, the water that we drink is in a liquid state. Water vapor is water in a gaseous state. Ice is water in a solid state. Freezing is a process in which a liquid changes to a solid. In particular, water changes to ice upon freezing. Freezing point is the temperature at which a liquid changes to a solid. A freezing curve is a graph that gives the temperature readings of the liquid and the solid at different times of a freezing process. The freezing curve, which can be obtained experimentally, tells us a lot about freezing. Let us obtain the freezing curve of water using this apparatus called the IFM kit. There is a metal tube inside this outer plastic container. One day before the experiment, pour salt solution into the outer container while leaving the metal tube empty. Insert a temperature sensor into the outer container to monitor the temperature of the salt solution. Then, put the IFM kit in a freezer to freeze the salt solution. On the day of the experiment, take out the IFM kit from the freezer. The salt solution has frozen and is now a chilling medium that can effectively cool the water sample to be injected into the metal tube. Inject 8 ml of water into the metal tube. Then, place an extension rod onto the IFM kit so as to facilitate the insertion of a temperature sensor into the metal tube. Now, use a data logger to monitor the temperatures of the water sample and the chilling medium. The green graph is the freezing curve. The red graph shows how the temperature of the chilling medium changed during the experiment. I would very much like the students to construct the concepts associated with freezing based on these two graphs. First, let us focus on the freezing curve. Why did the temperature of the water decrease rapidly at the beginning? Well, the chilling medium was very cold at the beginning, as cold as -15 degrees Celsius. As a result, a lot of heat flowed from the water to the chilling medium, causing the temperature to decrease rapidly. Next, the rate of decrease in temperature reduced significantly near the freezing point of water at around 0 degrees Celsius. Why was that so? Was it because there was no more heat flow from the water to the chilling medium? Not really, because the chilling medium was close to -12 degrees Celsius during this time interval, still very much cooler than the water in the metal tube. There was a substantial temperature difference between the water and the chilling medium, and therefore a heat flow out of the water. This is indeed an amazing phenomenon. There was substantial heat flow out of the water, but the temperature of the water changed only marginally. This brings to life something that students may have read from the textbooks, but may not have realized the physical meanings. For example, primary school textbooks provide information such as a liquid loses heat when it changes to a solid. We would expect that when the temperature was close to the freezing point, some water began to change to ice, thereby losing heat. The heat released upon freezing then flowed to the chilling medium. Therefore, in spite of the heat flow to the chilling medium, the temperatures of the water and the ice changed very little. This explains why this part of the graph is relatively flat. Secondary school textbooks introduce the term latent heat of fusion, which is the amount of heat that a liquid releases when it changes to a solid. Since this flat region around the freezing point lasted for quite a while, the total amount of heat that flowed out of the water must have accumulated to a significant level. This implies that the latent heat of fusion for water is not a small amount. Last but not least, the rate of decrease in temperature became higher when the temperature has fallen below the freezing point. The water must have completely turned into ice during this time interval. The ice was a solid so long as its temperature went below the freezing point. Therefore, the flow of heat to the chilling medium was purely due to the ice itself losing heat without the release of latent heat. This then led to a higher rate of decrease in temperature. Perhaps you would agree with me that there are indeed a lot of insights into freezing that can be gained from the two temperature time graph using the IFM kit and the data logger. Thank you very much for your attention.